Okay, welcome to Let's Get to the Marks, going through a physical chemistry A-level question on enthalpy change. Let's do it. Alcohols such as methanol, ethanol, and propan-1-ol are good fuels. We've been given their structural formulas. A student carried out an experiment to determine the enthalpy of combustion of methanol. Methanol was placed in a spirit burner and the mass of the spirit burner measured. The student placed 100 grams of water in a copper calorimeter and clamped it above the spirit burner. The burner was lit, allowed to burn for a few minutes. The flame was extinguished and the new mass of the spirit burner found. The measured temperature rise was 38 degrees. Specific heat capacity of water is 4.18. Figure 1, a diagram of the apparatus is shown alongside Table 1, which shows the measurements the students recorded. Let's get a little bit more of this into the picture. So, what is the question here, folks? Use the student's data to calculate an experimental value for the enthalpy of combustion of methanol in kilojoules per mole to the -1, 4 marks. We've been given the mass of the spirit burner containing methanol before the experiment, 214.02 grams, and the mass of the burner containing methanol after the experiment, 212.37 grams. And we've been given the apparatus setup. We've got a copper calorimeter, we've got water, we've got a clamp, we've got a thermometer, spirit burner, and some methanol in there with a wick. Okay, right. First thing I would do is grab a scrap bit of paper, grab a pen, grab a calculator, pause the video, have a go at the question, unpause, watch the walkthrough. Okay, let's get into the answers. So first thing I do when I'm approaching a question like this is I'd highlight any key points. So I'll be zinging through here. I'll be like, oh, enthalpy of combustion of methanol. We know that's kilojoule per mole down there. That's always in kJ mole -1. Methanol was placed in the spirit burner. Mass of the spirit burner measured. The student placed 100 grams of water. So what is 100 grams of water? It's the mass. So I've got M. Copper calorie, clamped it down. Bada bada bing, bada bada bong. Burn for a few minutes. We've been given temperature rise. Hopefully, you know by now the symbol for that is delta T. So we've got the temperature rise, delta T. And we've been given C, which is the specific heat capacity. And this should ring bells in your head. We are doing Q equals MC delta T. Now, Q is not actually our final answer, but it's going to get us at least 2 of the marks. So what we need to do is the mass times the specific heat capacity times the temperature change. And they've given all of those straight off the bat right here. Look, 100 grams of water. It's actually the mass of water is what the M stands for. So we want to do 100 times C, that's a really baby C there, times specific heat capacity of 4.18. So we're going to go 100 times 4.18, and then we're going to times it by the temperature change. Sometimes they give you the initial and the final temperature, or sometimes you've got to work out the initial or final temperature. But here they're giving us the actual change for us, so simplified things. So we just want to do 100 times 4.18 times 38, and that is going to give us 15,884 joules. Okay, now look at our answer. They want it, and it's always good to go down to the question and find the units they want. They want it in kilojoule per mole. So what's the first thing we need to do? We're going to change this into kilojoules. How do you change 15,884 into kilojoules? You know the coup. You divide by 1,000. And now we are going to get 15.884 joules. So next steps. This says mole to the -1. So I want to turn it into divided by moles. Mole to the -1 is in old money. Mole to the -1 over here is just kilojoule back in your GCSE days per mole. So when they write mole to the -1, that's what that means. So I need to divide that by moles. And how am I going to work out moles? Well, I'm going to come over here where I've got a bit of space, and I'm going to do mass over mR times moles. Now, you might get a little confused here and think you've got to use the mass of the water. No, that's what you're heating up. It's the mass of the fuel used. So I need to work out the mass of the fuel used, divided by the mR, times it by the moles. I can work out the mass of the fuel used by the mass of our container here. And then afterwards, when we've finished, that's the amount that has burnt off, hopefully. Of course, there are reasons why some of the other mass may have escaped, but we'll get into that later. So I want to do that minus that. So let's smash that in the old calc. So 214.02. God, that don't look good in pink. 212.37. So if I do 214.02 minus 212.37, I'm going to get my mass of fuel, and that's 1.65 grams. That's how much methanol we used. So I want to divide that by the MR of methanol. Methanol is CH3OH. So C's 12, O is 16, and H is 1. So I've got what? 4 H's plus 16 is 20, plus 12. Is that 42? Is it more than that? I don't think I can add up. I think I've lost the plot. 16. Oh my gosh, I've lost the plot. 17, 18, 19, 20. Oh my good gosh, it's 32. Jeez, that took me a serious amount of time to add up. Right, well, that is times 4. So that should have been pretty easy, right? 4 times 1 plus 16 plus 12, 32. Let's smash that in the old calculator. And if we do 1.65 divided by 32, we are going to get 0.05156. So 0.0515625. That's the amount of moles. That's N. And all I need to do now is divide that by N, which is that. So I'm going to do 15.884 divided by my moles. So 15.884 divided by answer. Bing! I get 308.05. Now, um, yeah, that is kJ per mole to the -1. Now, whether you want to round that down, three significant figures, so we could do that to 310, or I'll just leave it as 308.05. Sounds good to me. Two decimal places might be a bit nicer for that, so we could do it as that, or we could round it to 310. We'll see what the mark scheme says about that and then let you know. All right, and that's how you get your 4 marks. Right, let's move on to the next part of the question. So zinging down, suggest one reason other than incomplete combustion of heat transfer to the atmosphere. So we're losing heat to the atmosphere all the time. You can't prevent that. You can minimize it with heat shields, with polystyrene, with lids, with all of that stuff. Why the student's value for the enthalpy of combustion of methanol is different from the data book. So we've got a couple of reasons why. And it's maybe we didn't do complete combustion. Oh, it says other than incomplete combustion or heat transfer. So need to identify those. So definitely highlight those. So you've generally got 4 reasons why um you've got 4 reasons in this experiment why we're not getting the same data book answer. And it's normally heat transfer. So I'm going to go up and show you guys. So it's normally heat transfer. Let's zing up. But this one says like don't write heat transfer. So essentially, instead of all of the heat from the methanol going into the thermometer and causing our 38-degree temperature rise, we're going to get an underestimation because our temperature rise is actually going to be smaller. So our Q that we calculated at the start is going to be a lot smaller. And it's because heat is escaping into the atmosphere. Look, it's coming out of here. There's a flame here, but the heat is coming out of here. And so it's escaping out into the atmosphere. So it's not all going into that thermometer. We're not all going into the water, not causing that temperature to rise as much as it should. Another reason, which they said we're not allowed to use, is incomplete combustion. Incomplete combustion is when you make carbon monoxide or carbon particles. You'll know you'll get small black soot particles around the edges at the bottom of the beaker or the calorimeter. So incomplete combustion does not release as much heat. It's not as exothermic as complete combustion. So that's another reason why we wouldn't get such a big temperature rise, and it would why our answer doesn't match. But they've said we can't have that. So there are 2 things we can have. Methanol's an alcohol, and they are volatile organic solvents. They're going to evaporate. Even at room temperature, you'll get considerable evaporation. So we may have lost some mass through evaporation of the fuel. That's one of the reasons. And the other reason is here, what is this thing made of? It's made of copper, and copper's a conductor. So rather than putting it in insulating this is obviously you're trying to conduct the heat quickly into the water, but some of the heat goes into the copper to heating the copper. And here we go. So 2 possible answers. Some of the heat transferred into the copper metal or the copper calorimeter instead of the water. And then the other one is we had evaporation of the fuel. So there are answers here. Normally, you can also say incomplete combustion, or you can say heat transfer to the surroundings or the atmosphere. So evaporation of the fuel, as it's a volatile solvent or volatile organic compound, evaporation of fuel, and heat transferred to copper calorimeter. whatever. Ah, yeah, yeah, it's hot today. 2.3, the uncertainty of each of the temperature readings from the thermometer in this experiment is plus or minus 0.25. This gave an overall uncertainty in the temperature of plus 0.5. Sometimes they'll get you to work that out yourself. So because we took two readings to get a change in temperature, so we must have had an initial temperature and a final temperature, we have double the error because you get 0.25 when you read the initial temperature, 0.25 when you read the final temperature. So our change in temperature has a total error or uncertainty of 0.5. Calculate percentage uncertainty for this thermometer in this experiment. So we want to do total error, which is 0.5 over 38, and we're going to times 100. And that is going to give us our answer, which is 1.316%. It's actually 315 something, but you're going to round that to 316. Coolio. Right, 2.4. The student said correctly that using a thermometer with an overall uncertainty for the rise in temperature and plus 0.5 was adequate for this experiment. Explain why a thermometer was adequate for this experiment. Well, the reason is we got a large temperature rise. So the temperature rise was quite big. Woo. The temperature rise was quite large. So we had a 38-degree temperature rise. It's not going to look so great if it's a smaller temperature rise, but the bigger the temperature rise, yeah, then that means that level of uncertainty plus or minus 0.5 degree. Hey, if you're having a 38-degree temperature rise, plus or minus 0.5 degrees, not too bad. If you've got a 2-degree temperature rise, then your level of uncertainty is going to be a lot more. Look, imagine we had a 2-degree temperature rise. We'd be doing 0.5 over 2 times 100, right? We'd have a 25% error. So that would be pants. The fact that we had a 38 degree temperature rise means our percentage uncertainty is quite low. So the overall uncertainty of 0.5 is acceptable for that large temperature rise. Coolio. 2.5. The enthalpy of combustion of ethanol is minus 1371 kJ per mole to the minus 1. The density of ethanol is 0.789 grams per centimeter cube. Calculate the heat energy released in kilojoules when 0.5 decimeters of ethanol is burned. Give your answer in the appropriate number of significant figures. So once again, what I do here, I just highlight some stuff. Okay, so that is my delta H, that's my enthalpy change, enthalpy of combustion, whatever, put a little C there. I've got density here. I'll be given volume. So straight away, we can do density times volume gives me the mass. And why is that? Because density equals mass over volume. So I can do D times V and give me mass. Then we can convert this. We want to convert this back to just kilojoules. Okay. So let me explain. Right. We've got a total of 500 grams. No, we haven't got 500 grams. Let's work out exactly what our mass is. If it was 1 gram per centimeter cube, we'd have 500. Right. My density, I need to align my units. So I've got 0.789 gram centimeter cubed. Now, I'm going to multiply that. That's my D. I'm going to multiply that by my V, which is 0.5, but the units don't align. Look, my volume units do not align. So I need to times that by 1,000 and turn that into grams. Sorry, off my rocker. Turn that into centimeter cubed. Now the units align. This is divided by centimeter cubed, and that is centimeter cubed. So we're just going to be left with our mass. And our mass here, which should get us the first out of 3 marks here for calculating the mass, 0.789 times 500. That is going to give me 394.5 grams. So I have 394.5 grams of ethanol has been combusted and released that. They now want me to work out how many kilojoules that was in that volume of ethanol. So this is the mass that released that. So I need to find out, I need to get rid of this mole to the minus 1. And what I'm going to do there is, I'm going to do, I need to find out the moles, don't I? Yeah, so let's find out the moles. So we're going to divide this by moles because mass over mR times moles. And we're dealing with ethanol this time. So I'm looking at C. Did they say ethanol? They said ethanol. C2H. Oh, yeah, there we go. So I've got 24 plus 5 is 29 for the 5 H's, and then plus 17. Oh, my days. Don't ask me to do maths. 34, 43, 48, right? Is that 48 or is that 46? That's 46, right? 17 plus 5 is 22 plus 24. Oh my gosh, 46. Nearly screwed that up. Right. So why am I dividing it? I'm trying to find the moles, you Wally. So I'm dividing it by the MR of 46. So essentially, I want to find moles. And you might say, why do I want to find moles? Notice this is kilojoules to the mole minus one. The unit they want our answer in kilojoules, right? They want our answer in kilojoules. We need to get rid of mole to the minus one. So I need to times by mole. If you times mole to the minus one by mole, you get rid of the mole to the minus one. And that's what we need to do. So we're going to go 394.5 grams of mass. We work that out by density times volume, divided by the MR of ethanol, which is 46. That is going to give me 8.576, and that's my amount of moles. So what I'm going to do is multiply those moles by minus 1371 kJ to the mole minus one. And by doing the times in the moles, and that's dividing the moles, you're cancelling the moles out, and we're going to be just left with the kilojoules. So let's do that. What have we got? 8.5, my days, 76 times minus 1371, and that equals, I'm getting my reading is minus 11,757 kilojoules. Now it says appropriate number of significant figures. At A level, they love you to do 3 significant figures, people. So I want to round this to 3 significant figures. That 5 is going to push this up to 8. So it's going to be minus 11800. We only want the first 3 numbers that are important. They're the 3 significant figures. So it's 11,800 instead of 11,500 and 11,757. Jeez, I longed that out, peoples. There we go. 3 marks.
If you push the button.
Like me.
Would you like it?
Like. I like it. You're still here? It's over.